some questions that we got from the online form that was shared on the YouTube videos, on the abstract section of the ECCV text, and on the list of tweets I put online. And we don't have that many questions. We have a few there. And then please feel free to ask questions. Right? That's the message here. So the whole purpose of us being awake and present here, trying to speak hopefully with not too bad sound, is to be able to have a discussion and to exchange ideas, and hopefully to answer some of the questions you may have, either from the field in general or specifically from having seen the videos that we recorded. Okay, so can we record? So yes, we're recording. And then I had on the videos. Okay, so maybe what do you think, June? Do we start with the, so now we have basically 3 sources for questions. Need to figure this out. Do we start with the live questions, or do we start with the form questions?
Maybe the live questions first, because they're the people who are here for sure. So
all right.
Yeah.
Okay, and then the ones from the form that will be recorded. All right. I'm really trying to move to have all the questions visible in the same place, but I'm not merging yet. Okay, I guess I will just have to move around. Okay, so maybe let's start with the very first one that we got on the chat, and then we move on to the Q&A part, and then we move on to the form questions, and then we'll move on to the extra content that we anticipated in case people were a bit shy with the questions. All right, so the first question is, you mentioned that methods were not getting better or a decade. I'm not sure what that means. But
yeah.
CAM is the earliest explored. Can you mention earlier work that performed as well as CAM?
I think that question is for me. So we had a paper on WSOL, object localization. And one of the key arguments was that when you do everything right, all the evaluations right, then CAM turns out to be the best method among methods in 2016 through 2019. And I think Guy is asking if there was any method before CAM, which is solving the same task, and if any of these were working better than CAM. About these points, actually, we did some further analysis along this line. So we looked at this so-called image saliency, where we look at the image gradients. So what's the local response of each pixel for the final classification output? Well, basically the gradients with respect to the class of interest, right? And you can also use this image saliency as a cue for localization, but in our evaluation, it was performing worse than CAM. There are some other methods, I believe, for example, using global max pooling instead of global average pooling, as in CAM. And this max pooling idea was before the CAM idea. And we don't have a comparable result. We haven't set up a good evaluation setup for measuring the performances apples to apples, but I presume using max pooling will be worse than using average pooling. But it's going to be better to have this analysis as well at some point. So CAM is a simple method that's been used a lot in different literature, and it turns out to work quite well.
And it's also the basis for many other methods, right? Many methods take CAM and then tune it, modify it, improve it in some way. So most of the current techniques that you will find in the last, since CAM came out, basically, most of them will be CAM-based or CAM improvements.
Yeah. So CAM is relevant in many setups. Yeah.
So do you know how you control which screen is being seen? I'm used to different software. Usually you control what is being seen. Do you always see my share screen, or do you always see yourself? I'm not sure what is being shown to the other people.
I used Zoom for a bit, and I think when you share a screen, then you're forced to see the screen only.
I see.
But you can, I think, still see other people's video as a small thumbnail on the right top corner. But I think that is not the case for this video chat. I think this is more like the tutorial or conference version where there is a speaker and there is an audience.
All right, we'll see. So that means that what I see is not what's being recorded. That's a bit unusual.
I think the share screen is being recorded at the moment.
All right. Well, so our voice is in off. Keep calm and ask questions. That still works for me. And then next time you answer, I will probably show your face then, so that your face is shown recording. All right. Thanks for that question. I think that was the first one. So we still have 30 attendees who are sticking in. So thanks for joining us and staying in the session. So please don't feel shy. No, we have room for a lot of questions. So just ask the questions. There's no, as long as it's related to weekly supervised learning in some form, there's no out of scope question, right? It's a tutorial. You can ask very basic questions. You can ask very advanced questions. We're here for answering your questions. So let's see, next question. So from Aditya, it seems that prior seems to play an important role. Many methods benefit from better initialization from CAM. So I guess this refers to these seeds. Are there more robust way of initializing from CAMs, such as the results don't depend as much on the initialization? So I think there's like a family of papers specifically on these questions, right? Where they will all claim that our way to get something out of CAM is the better way. I think regarding the second part of the question, they all are very dependent on that initialization, right? It's like, almost all the methods start from giving the noisy signal from CAM, trying to get something that is confident, and then either the noising was confident or building up, assuming that there's no more noise, and then building on top of that. So in that sense, there's no avoiding that part. And then regarding the different ways, I think in a sense the evaluation paper from June kind of hints on that, right? Many of the papers actually, most of the work is saying, okay, starting from the CAM raw output, how do I get something that's better? And then when you look in the details of how they evaluate, then you realize that maybe some of the claims are not as clear as shown in the paper, let's say that way. So I don't know a method that I will be very confident saying, this new variant is definitely the best variant you want to use. I think the theory is a bit open. The typical way it's done is just with a threshold, and that works well enough for most techniques, for most papers. And then a slightly better version of this is when you use quantiles. So you basically take the top end pixels from the CAM. And I think I can dig maybe as we go in the chat. There was a recent paper who actually was only making a point about how to best use CAM, and of course show better results, and they seem quite sensible. However, remains the question if the evaluation was well done. So I guess since June made his paper, I was worried from the new papers until it hasn't been reproduced or re-evaluated. I'm not so sure about the claim, but I would say it's an open question, and there's like a whole series of papers who each claim to be the best, and I'm not aware of one or haven't seen one. When I read it, I was like, oh yes, I'm very convinced this is definitely better. What do you think, June?
Well, I agree with you in most points. I also want to add that when you use CAM as a seed or initialization, probably it's better to focus more on precision than recall. That's probably a way to get more robust initialization than trusting CAM too much for it to return all the object extent at the beginning. If you just treat CAM as the seeds for just getting the discriminated part of objects, then I think CAM is still very robust and in many cases quite correct. Although there are also many cases where even the max point given by CAM is wrong.
Yeah, that's definitely the case. In that sense, also is to be reminded that together with given the CAM output getting the seed, a lot of the other family of papers related to CAM actually think of how do you get a CAM-like output by modifying either architecture or the training, such that is better. In a sense, I think these are kind of the two main ingredients of CAM, right? How do you get the class activation maps, and then how do you out of that extract confident information or use to train whatever is downstream? And I would say in practice, the two ingredients are just, I would say, about equally important. Like you will see that most papers get quite a lot of gain by making the training better or the change in architecture better, so that as June said, you have this better localization. And at the same time, you still need to have this carefully tuned thresholding aspect in there. But I think the initial question was about robust, like something that would be, I understand by robust in the sense that you are confidently will work in most scenario. And I will say actually not really, right? Most of the methods, if there's anything, I would bet that they're more brittle than robust. And as June paper shown in the evaluation session, if you haven't seen that video, the evaluation video talks about this. It basically probably tuned to the scenario where the authors are showing the results.
Mm-hmm.
All right, so let's try to move on to the next question. Okay, we should check out our own videos. I think we can do that.
Yeah. There was another question from Guy again.
Yes, yeah, I'm watching that question. Let me see. Also, I'm trying to check the chat. See.
Mm-hmm.
Okay, I think the chat we have answered all the questions, and the resolution of the screen to do streaming upload overhead. Sound problem. How is the sound from on my side, June? Is it okay? Is it okay or not really?
It's very good.
Oh, no, it's good.
Yeah.
So that would mean that maybe. Okay, we'll figure out.
Yeah.
Let me, yeah, exactly. Let me know if something really goes bad. I have high resolution screen, so that might be involved indeed. Let me know if it breaks again, and that way we adapt. Maybe it's better that if you stream instead of I stream. We'll see. If it's good now, let's keep it good. Mm-hmm. All right, so let's go into the GOI question. So I was very impressed with An et al. CPR 19. So that's the RNN method, which was presented in the weekly supervised segmentation video towards the second half of that video. It also relies heavily on CAM, that's totally true. How do you think they will compare on the level playing fields when applied the same evaluation as you have applied? So here referring us to June presentation on the evaluation. So I would say it's a bit of a different beast in that sense, because at least the way I understand June's and colleagues' work is this aspect that the comparisons are not fair because the tuning has been not fair. However, the main point of the RNN paper is not so much about that is better in some aspect than the other ones. It's that you can do something that wasn't done before, and that's kind of the aha. Oh yeah, that's what makes the paper interesting. In some sense, which exact number they get is not the point of the paper. The point of the paper is they can do it at all, and they can do it in a way that is not a total disaster. So in that sense, I will think for that paper, I'm not particularly worried about the evaluation, because anyways, if you look at the instance segmentation evaluation, they don't have really a proper comparison point. So they just compare to other techniques that did some form of supervision to get some form of instance segmentation. But the best of my memory, they compare very disparate methods with very disparate supervision. So it's not even meant to be an apple-to-apple comparison. It's just meant to be look, our number is not horrible if you put it in the spectrum of other numbers that have been published for this task, or no, this similar task, in the sense that the aim was the same, but the supervision might have been different. So yeah, I would think it can, the key point of, because, okay, maybe let me one step behind. It's like, I'm old enough to have reviewed a lot of papers and seen a lot of paper at the conferences. And one of the, I think, because the field is young, I think a lot of the young authors have a strong bias towards numbers, and that the numbers matters a lot. And June paper is a reminder why you shouldn't be too focused on the number, because experience tells that, and again, I think June talked about this in his presentation, that no, this is not specific to weekly supervised learning, right? Almost every area of computer vision, and I'm willing to bet that most areas of science have kind of cumulative errors on how they evaluate things, how they measure things, and then they have a aha moment where they clean it up and then kind of reset the slate and keep going. So this phenomenon where the evaluations get rotten and then you have to refresh them so they get better, I will suspect it's like a never-ending quest. This will keep happening. So in that sense, when you see a paper, you know that, okay, this 2% is like a formality, right? Sure, they need to be an abstract, a middle, a conclusion. And of course, the numbers that you show need to look a bit better or at least comparable, but it's a formality, right? What you're really looking as a more senior member of the community is like, is this an interesting idea? Is this something that I believe people will be able to build in? Is this something that provides me a new insight? So in that sense, I think the R9 paper fits very well that bill, in the sense that it's an interesting paper, it's an interesting idea, and sure, they get some number, but the numbers don't matter so much in the big picture, because you anyways suspect all the numbers to be somewhere wrong. All right, that was my last comment on that.
Mm-hmm.
So if that's good, then let's move on to the next question. Can you read it, Jun?
Sure. It's another question from Aditya. There are several papers in literature that try to train a network using noise labels. Can similar ideas be used to treat CAMs as noisy seeds for the WSL approaches instead of threshold-based CAMs? Yeah, I think this is partially done in many papers. So I think I don't know if I can say usual strategy, but at least I've seen some cases where they start from before that, let's confine this task to weakly supply semantic segmentation using CAMs. In that case, what many people do is they first train this first iteration network using CAMs as seeds from high thresholds, high confidence localization signals. And then based on the predictions of the first network, they generate this second iteration pseudo labels, and then maybe correct the second pseudo labels a bit using the CAM outputs or other types of priors like boundary information or stuff like that, and you keep iterating. And what is partially done here is the decision of whether you trust or not the outputs of the nth network, because they will be noisy necessarily, because they are not ground truth, like true segmentations of the objects. So you need some kind of decision of whether your pseudo labels are correct or not, even in this case. And I guess your question is if you can do this even further back at the seed level. And my answer is yes, probably you can do that. But there should be a good way to tell if your CAM is good or not. And for this, you need some kind of other extra information from outside, I guess. because if you have a way to know that if your CAM is good or not, then you're already using that knowledge, you can already improve your CAMs. And yeah, you see the logic is cyclic. Like if your CAM was good enough, then you can improve your CAM and improve the noise. But without extra information, this kind of goes back in a loop.
Yeah, it's similar in that fashion, in this aspect of you can choose to improve how you use your CAM, or you can choose to improve how you make your CAM, right? There was this this presentation, I think it was coming in here, right? Who was pushing this idea of trust the features of your convolutional network in the mindset of like, especially at the beginning. I think now this idea has become more pervasive, but there was this tension between, do we take some form of neural network and then we have a lot of tricks on how to use the output so we can generate, in this case, detection? Or what Kaiming here was saying is like, forget the tricks, just train an end-to-end neural network and push the network to be the biggest, the fattest, the better trained possible, so that the network figures out everything that is to be figured out. And I think a similar thing you can think of for CAM, in the sense that you're wondering, well, should we get this CAM output as is and then try to use all the tricks available to reflect the fact that it is noisy and then use it? Or should we just push the CAM itself, the activation maps, to be as good as possible? If I had to bet in which strategy is going to pay in the long term, I would think that improving the class activation map is most likely to lead to better results in the long term. Just because it rides the wave of architectures better. So as architectures get better, that work will get better. As the training data and the kind of available training tasks gets better, then that part of the work will get better. While whatever you use as a way to use the CAM despite the noisiness will have strong, at least some level of assumption of the kind of noise that you have. And I would suspect, at least in my experience, that noise you will get is specific to the setup you have, like specific to the architecture, specific to the training set. So in that sense, it will become brittle to the next generation of architectures and to the next generation of training tasks, while the first part is not. So I will definitely agree that it's an area where it's interesting ideas to be explored, but I wouldn't, like, if I had to kind of spend energy on one or another, I would suspect it's good to use out of the box or like well-established techniques to handle noise, but I wouldn't, like in the short term, I might consider pushing develop. Within the long term, I don't think is the best strategy. I guess maybe that's what I can say. I want to make a small parenthesis and go back to one of the previous questions. Let me see now if I can share the screen again, and please let me know if the noise goes really bad. So one of the papers I had in mind regarding, there was an early question about kind of how to use the CAM output and should we use threshold or not. So there was an ECCV paper. I think one of the things we want to do in this session, if we manage, is to highlight some of the interesting ECCV papers that not all of them were in the talks. And one of them that did pop in my radar was this paper, which is specifically about, the only point of the paper is say, like, given the class activation maps, what's a better way to extract information out of them? And then basically claim that there's like 3 issues that you have to solve. And I'm going to go into all the details of the paper, but they have a specific section on how you should do the thresholding. And they have their own claim on how the thresholding is better. So the caveat that of Jun's evaluation still holds, that maybe the evaluation is not completely fair. And in a sense, now I want to see this work re-evaluated, and then I will trust the results. But it's the type of papers I was mentioning that try to focus on at least try to have a clean argumentation of what's the better way to extract the information. And if you're interested in this question, you should definitely check this work as a reference point. And I think it's, in some sense, it also relates to the question we're just answering right now. Mm-hmm. All right, so let's hope that was a good answer for the previous question. And now we can move on. All right, keep going with the questions. We do have with quite a bit of time, so I think we're good. We still will allocate, I think, at when we reach the hour, so that will be at 10 o'clock in my time zone. So when we reach the hour, we'll definitely switch to the questions from the form to make sure we answer them, and then we can switch back to live Q&A. That makes sense to you, Jun? Yeah. All right.
So there was,
and I don't know what happened to Hagen.
Oh yeah. Yeah, I didn't get any email from him yet.
Okay, I guess he had a trouble because he knew about this.
Yeah.
All right.
Okay, so there was another question from Guy. It could also work as semantic segmentation when applied to a single class image, and then compared to the object localization works in numbers. I think I'm missing the context of this question.
What is it? Yeah, what is it? Can you, if you're hearing us in the chat, can you ask, to the previous question I had, can you write in the chat what was the previous question you had? CAM, I think it's just referring to CAM.
Yeah. Oh, no. He was talking about the weekly supply instance segmentation work.
Oh, I see. Okay. Could it also, so is the RNN paper, could it also work as semantic segmentation? Oh, yeah. So in the RNN paper, they do have evaluation results for semantic segmentation. If you can do instance segmentation, that is a harder, richer task than just the semantic segmentation. So you can take that output straight, remove the instance information, and evaluate it as semantic segmentation. So they do evaluate that, and of course they do show they have competitive results there when compared to methods that only use image level labels. And as I mentioned in the video, again, with a reminder that that paper is one of the very rare papers. There's some previous one in semantic segmentation that were also pure, but most of the latest good performing methods actually are not pure in the sense that they're not only using image net pre-training plus the target dataset image level label supervision training, but almost all of them use some form of boundary detector or saliency information or handcrafted saliency that then is injecting extra information. So for semantic segmentation, RNN also works, and it doesn't need to be a single class. It can also be multi-class, and it works fine and relatively well on that. If you have one thing to mention respect to RNN, which echoes the things we were discussing before, is that if you look at the code base, they do have hyperparameters, right? They do have some parameters in there that work for Pascal, and they have a different set of parameters that work for Coco. And well, right, where those parameters come from, how are they tuned, how much they matter. To the best of my memory, the paper does not have a sensibility analysis of all those parameters. So the better science is done when you have a sensibility analysis, but that takes a lot of efforts and more computational resources that most people have, and it's not demanded from reviewers in papers in the conference today. So it's not there. So it does work. It does work well. It relies on some hyperparameters and remains unknown how sensitive it is to that. But at the high level, it's still a really cool paper that I think everyone who is interested in this area, it's a worth read. It's like it's inspiring paper in that sense.
And there was an update question from Guy as well. So he's saying he wanted to ask how it evaluates compared to CAM in a leveling playing field.
Well, it's not directly comparable in the sense that the RNN paper, so from Anne et al. From CVPR 19, takes CAM as a kind of a starting point and then builds on top of that. So it's expected to be significantly better than CAM. Let me again, we have a share screen. Let me.
Yeah, but also CAM is only given when you give the method. Well, it's given only per class. So per class, you're going to get a single heat map. And for semantic segmentation or instance segmentation, you somehow have to combine all these signals from different classes into a single label map. So it's non-trivial how to go from CAM outputs to semantic segmentation outputs, for example.
I guess I was assuming it was considering just like a baseline where you take these thresholding techniques and then you do the argmax of the scores and then you just train a semantic segmentation network with that. Let me see. Let's share the screen. Okay, still a bit not used to sharing the screen in this configuration. Let's see. Okay, now, so this is, can you see it well? This is the RNN paper. Do you see it, June?
Yeah.
So they do have a section where they compare to their interpretation of raw CAM for okay, so they have it for, I'm not sure what they mean here by the pseudo instance segmentation, but by some evaluation metric, which doesn't matter much what it is. I think it's the one where they assume that the instance assignment has been done correctly, and then it's like the best IU you could IU you will get out of that if it was done correctly. But again, it doesn't matter. The main point is that raw CAM is terrible, and then when they add the special sauce, in this case the class boundary estimations, then they get a huge jump in this metric, right? Factor 3 improvements. And you can also compare SEC in a sense, which is also was presented in my video about weakly supervised segmentation. It's kind of a fancier version of CAM, and is a relatively well established a fancier version of CAM. So they have CAM plus extra ingredients, which you can see on the video, the explanations, and that serves as an upper bound for CAM. So whatever you do with CAM, you're probably not going to get better than this, and you can see that they have a healthy 10 extra points improvement on top of CAM. So I think that provides in their setup good empirical evidence that that they're better. And there's still always the question mark after June paper. I was like, well, but did all this paper tune CAM well, and maybe they could have tuned CAM a bit better? And yes, that might be the case, but you can assume that most of these papers were pushing the envelope by themselves. So I will say I will expect the results to hold, in the sense that it is better because it's better using the information available and the priors available. So yes, it worked for semantic segmentation, and I think it is better than just ROCAM, to the best of my understanding.
Should we go on to the next question then?
Sounds good to me, yeah.
Yeah. Another question from Aditya. I have observed that in several iterative approaches, the self-driving sort of a loop kind of, it kind of forms a loop, right? That reinforces the error that it makes in the first round. Is there a paper that focuses to recover from that? So should I start answering, or will you do the answer?
You can start and then I will add.
Yeah. I think many papers are doing that. I think this is the gist papers are trying to address in weak supervision literature, as well as in, calling this self-training kind of rings a bell for me in the self-supervision literature, where people also do that. Like they train this moving average network, exponential moving average network that's sort of acting as a teacher network to train the current iteration network, where the teacher network is just an average of the previous few iterations. So it's kind of trying to train itself from the previous versions of itself. And the question is if this kind of approach is really going to work. And intuitively, I would say it's not going to work in the out of the box, because it's sort of looping itself back, and there should be some extra information needed to make this run. The way I think of this is also as a perpetual motion system, where you claim that something works out of itself, but in effect, you have to add some extra energy to make this run forever. And I believe papers are focusing on how to add this extra information in general, and how to iteratively improve itself using this extra ingredient effectively. Yeah, I was actually thinking about this paper that Rodrigo is showing. So probably Rodrigo can explain this paper better.
And let me take a knack on that. So you still see it? I'm still confused at what is being shown and what is being recorded, but we'll figure out.
Well, I do see your slides on this box,
on the screen.
Box to segmentation work.
All right, we'll figure out. Worst case scenario, the second slot will have a different recording and we'll leverage that. So I agree with June that in a sense, this is kind of a central theme in weakly supervised learning, but it is one of the things that is fundamentally wrong, but we get away with it, right? So, and welcome to computer vision. There's a lot of things within computer vision that are known to be fundamentally wrong, but work. And then until we figure out something better, that's what we use. So for the ones who might have not seen this part of the talk, I'm just going to repeat it briefly, right? So I consider this a baseline paper of which I was a co-author. And the idea is super simple, is to say, like, if you're going to try to train for weakly supervised segmentation, and you start from bounding boxes, you think of the bounding boxes as a noisy label, right? Back to also the previous question about what can you do with noisy label. And the idea we wanted to explore is the dumbest idea ever, right? It's like this is one of my personal passion in computer vision. I like to do the dumbest thing ever and show that it works better than previous paper. And here the dumbest idea we had was like, let's do nothing, right? I have hard troubles coming up with dumber ideas than that. So let's do nothing. And we just train straight on with that. Default parameter, default network, just train. And the observation was that the outcome of it's a failure, right? The method is being asked to output squares. If it was a good learner, it will explicitly output these rectangles, but it fails to do that and actually learn something different. And to add to what I already recorded on the video, I think this links to a different idea that people might be not so familiar with, which is a deep image prior. So deep image prior was let me find it back, since we're doing this live, was a CPR 18 paper where I really like this paper. I think this also people in the image cleaning community liked. And we might be wondering, what's the relation between image cleaning and weakly supervised learning? Give me a second, I will get there. So the idea of the deep image prior paper is to say, we're going to take a single image that has something noisy, and we're going to train a model to reconstruct the image. So it's like single image, single network kind of work. And they show that depending on how long you trained, then you get different type of images, right? So like here, I guess you can see here, you have some kind of noisy image. And then if you train a little bit the network to reconstruct the image, it gets something very blobby, and then something better. And eventually it gets to be exactly the same. But in between, there's a transition where it's actually smoother and still looks the same. So the insight of this paper was to say, like, the architecture we're training has some kind of prior on the kind of structures it enjoys to reconstruct. And this idea is being extended in one ECCV paper, which I actually liked. It's probably one of the papers I would recommend as a highlight, where they say, oh, wait, but the architecture prior of this method, of this previous paper, it was arbitrary, right? Whatever was a popular network design, which I don't remember was BGD or ResNet. But now we have architectural search techniques, so we can actually optimize architecture such that this task gets to do exactly what we want, right? So better super solution, denoising, or whatever you want to do with it. So this ECCV 2020 paper that actually searched the architecture that when you train to reconstruct the single image does basically does the kind of reconstruction that you want to have, so that in this example, let's say it denoises the image better when you do some kind of early stopping. You say like, give me the architecture that if I train for 1,000 steps, give me the better image reconstruction, right? It's kind of a crazy idea. And now linking back to weakly supervised, this is the same phenomenon to the best of my understanding, because the reason that this network failed to learn a rectangle is because the architectural priors are against making rectangles. It's tried to do something else. And what this network tries to do is to find whatever is at the pixel level consistent between the input and the output. And this is a somewhat now well-established observation, is that neural networks classification is shockingly, at least the modern architectures, they're shockingly robust to noise. So you can train with 10% noise, 20% noise, 30% noise, and with high likelihood, the training will go perfectly fine. It will learn a good signal. And here is kind of the same. So at the pixel level is a classification task. Every pixel that is consistently looking like a horse will be a positive signal. And every pixel that goes with background, well, if the backgrounds are diverse, there would be very noisy signal. It's like all kind of backgrounds appear, so then it gets learned less well. And that is the reason why this network is not suitable to learn rectangles. It doesn't have the architectural structure to learn rectangles, and it tends to have this denoise version. And then, as June mentioned, then you can do this and loop it, and then it will keep denoising and keep denoising until it reaches a fixed point in this kind of iteration steps. In this looping process. So in that sense, the fact that we can denoise from here to here is exploiting architectural prior that is being baked into the network. And that is back to the presentation I did, is like one of the ways you can bake in priors that is being exploited. And in some sense, I think you can make the argument, I don't think it's a great paper, I don't think it's worth spending months of your life into this, but you could make the argument that these two ideas could be put together. So they should be, it is possible, for sure, that you can do a neural architectural search in the similar spirit of this paper, such as this process gives you the best denoising segmentation, the best denoise segmentations for the segmentation task. I think clearly that should be doable. It turns out that the current architecture really are quite good, so you can exploit that. And as we show in this paper, that actually does work quite well, like surprisingly well. So what I'm trying to say that back to the spirit of the question, the loops don't really reinforce the errors, right? Actually, that is the empirical evidence and the theoretical understanding show that is not quite the case. It's actually there is, because of the architectural priors, there is a denoising phenomenon that has been shown in multiple papers, either like in this a deep image prior and or I think this is simple does it. That's the name of this paper, and that is being exploited. So Some errors are structural or repeated or fundamentally ambiguous, which is maybe one of the topics we'll eventually get at. And those don't get the noise, but things that would be modeled as noise gets removed. And that's why this self-training actually works. It's one strategy to bake in a prior and using that prior to the noise. Right, that was my rant on that point. All right, so let's see. Let me try to pause the sharing. Maybe if the image gets frozen, let me put back this. Please ask more questions. Otherwise, we'll switch to the form question, and we'll check also just one more time if we do get questions on the YouTube videos. I don't have an easy way to do that anymore. Okay, I won't check the YouTube videos. All right. Because I closed the windows, so I don't have an easy way to do that.
Yes.
So I think that was the round. So thanks a lot for all your questions, especially I guess Goy and Adjeta. Let's go into the form questions, and I will check that also one more time if you didn't get new ones in the meantime.
No, we didn't get any new ones.
Okay. Let's go into that, and then we have extra content also that we prepared, just like topics we thought would be relevant to discuss beyond what was recorded. All right, so I'm switching to the document, June, in case you're wondering. Okay, so the first question we got from Anonymous was, I'm going to read it loud. If you have a certain budget to construct a dataset for image classification, detection, or segmentation, then what is the best strategy to get the best quality data and the best performance? Out of four options that the questionnaire puts is the A, few data with precise annotation. So like basically a little of fully supervised data, lots of data with weak annotations. So weakly supervised, traditional weakly supervised data. C, crawl data, so extremely large but unsupervised. So that will enter into the semi-supervised setup. Or A plus B plus C, basically a combination of these three. Okay, so I guess both June and I have some comment on this. Do you want to give it a shot to begin with, June?
Okay, that makes sense. Okay, so I think this question is really interesting. Like this is the kind of a choice you have to make in many practical setups. Like you have a lot of unsupervised data or weakly supervised data, and then you have an option to annotate a few fully supervised samples for this task. But then you have to spend some money and time and people on this. So to begin with, I'd like to point out that it's not too expensive to collect high quality samples. Meaning something close to fully supervised samples. So for example, you can collect, like for the task of localizing stuff, you can collect bounding boxes. And collecting bounding boxes are not too expensive as you expect. Maybe sometimes it's even cheaper than collecting class labels per image. Because for class labels, you sometimes have to go through the list of, I don't know, something like 1,000 classes, for example, for ImageNet. And that takes much more time than just drawing bounding boxes on likely objects in image.
Actually, let me interrupt you on that one. I think this is one of the little dirty secrets of image labeling, which is it is true that often enough the image level labels is the most expensive part of the process. So if you have very few classes that you can memorize, like 10, and you can keep it in your mind, then no, then everything else usually is more expensive. But as soon as you have more classes that you can keep in mind easily, which in my spirit is like around 20, 30, then image level labeling are very likely to be the most expensive part of your process.
Yeah.
And modern datasets try to expand the number of classes to hundreds and thousands, and then it clearly becomes the dominant aspect of the labeling. But it's a secret.
Yeah, so that kind of brings us to the question whether what is really cheaper? And sometimes the so-called expensive labels are actually not that expensive, but very effective for your task. That was the case for weakly supervised object localization. For example, you can collect a few few samples for a class, such as one sample for a class at random for the full supervision, like bounding boxes, then you get much better result than doing all the hyperparameter tuning and all the engineering cost, spending all the engineering cost on finding the right setup for weak supervision, full, like perfectly weakly supervised case. And that was the results shown in our CPR 2020 paper. And just a bit more about the engineering cost by using only weak supervision. If you only use weak supervision, then you are very much likely to introduce a lot of hyperparameters. Most of them are, well, many of them are thresholds, because you have to make a choice until which point you trust the outputs of the model for maybe for intermediate steps or for the final outputs. And for making those choices for thresholds takes a lot of engineering, because you have to do this meta search over the hyperparameters, which are not easy to just do gradient descent, right? So you have to keep in mind that engineering cost might dominate the annotation budget in many cases. And the questioner also mentioned crawl data. And one should be careful about crawl data, that you have to go through a lot of denoising process to make it useful. By useful, what I mean is by using this crawl data, it should help improving your performance. But if you just right away use this crawl data, it will most likely degrade the performance. And you have to do some non-trivial work on cleaning up this data. So I would suggest, like, I feel like for really solving your task at hand, the full supervision is necessary. At least a bit of full supervision is really necessary to solve this problem, at least to make an evaluation benchmark, because you have to know when you're really solving the problem, right? And for this, you need the full supervision to make the evaluation. And if you're going to prepare this validation set for determining you're actually solving the problem, then you can share a bit of your evaluation set for fitting your model itself as well, and improve your performance a lot based on that. And after that, if you have other sources for supervision, like weak supervision or web crawl data, then yes, why not? You can use them. And then I think an interesting direction you can take in this case is to select important samples that's really going to give you a lot of information about the task, and only label those ones to save costs. And for that, I think Rodrigo's talk is really useful. This human in the loop idea of selecting samples to annotate to minimize the human labeling cost. Yeah, so my answer is use a bit of full labeling, full supervision, at least, and then try to incorporate the other sources like weak supervision or web crawl data.
All right.
Yeah.
So let me complement that. I see Hakan somewhere online, so maybe he will join eventually.
Okay.
So let's see. So let me complement the point. So I fully agree with the general spirit of June comments, and let me build a bit on that. So the first point that you mentioned is aspect of full supervised might be cheaper than you suspect, and then the engineering cost needs to be accounted for. And I fully agree with this. Like it's there's also a very big gap between the cost of annotators and the cost of engineers, at least in the setup where I live. I live in one of the most expensive countries in the world, and the annotations usually are not done on those countries. So if you have like 3 months of engineering, 3 engineers for 1 month, that would be a lot of annotations in a dumber way, right? And I think what dominates, as also June echoes, is setting up the process. Whatever your way to do it, right? Setting up the process becomes very painful, expensive, and difficult, especially when you take into account organizational dimension, not just the software, but like needs to be like people organizing this whole thing and then having a way to pay these people and so on. And usually that dominates quite a lot. And as June said, I fully echo this, is like, as soon as you have the process set up, then why not exploit it more, do more with it? So I guess the two caveats I would like to add on that idea is, the first one is that it is true that fully supervised would be cheap for some tasks, but then there might be other domains or tasks where actually it is quite expensive. I think my personal example is I was part of a team who did cityscapes, and cityscapes is famous to allowing a lot of papers to brag about how fast they are, because cityscape was 1.5 hours per image, with, again, these caveats of why it was so slow and so on, but it was 1.5 hours per image, right? So it's a lot of time and it allows to do, and this was the case because it was very high resolution and it was very high quality, and we really pushed the envelope on that. And I think that became the trademark of cityscapes, and that's why it's one of the reasons it became a very useful and very used data set. But there are, if you do many class instance segmentation, that is very expensive. It can get very expensive. And also the other scenario where it gets expensive is when you have images which need some expertise to interpret. So if it's not anyone who can do annotation, but needs to be someone specific, then already that right away becomes way more expensive, because they need to be trained or they need to be found, and their time will be more precious because they have an expertise that is not readily available. That's why also you see a lot of papers on weakly supervised learning in the medical domain, because that's where the annotations become expensive because of the access to the expertise. So there will be some maybe slightly more niche domain where what was previously discussed doesn't hold, and that's a prime case of want to use weakly supervised learning. And the other case where I think it matters is which also June was echoing, is the aspect that even if the annotations are relatively cheap to do, especially compared to the image level label, but that's a secret. The tails are hard to capture, right? So you want to scale up the volume so you can start capturing the tails, the rare cases, the stranger instances. And when you do that, then because you're hunting for the tails, you're somewhat doomed to cover a lot of repetition. And you don't want to spend a lot of money into repeating annotations. So that's one of the ways to kind of get away with that, is to just do weakly supervised at scale. So, and then if you have some repetition, well, first it's less likely because you're doing weakly supervision. So it's less likely you're explicitly repeating the same instances in the same way, depending on the specific setup you have. And even if it was the case, when it's still cheaper because you're having at least a constant factor reduction in the cost. So it's, when you're looking for scaling up and looking for the tails, it's a way to reduce the cost. That's when also you start considering weakly supervised annotations. Now, I will also say that, for instance, that also holds not only at the instance level, the repetition, but also at the notation level. So if you do a box, in a sense, each one of the corner of the box is telling you different information about the image. But I will argue that when you do segmentation, the moment you have a brush, then two nearby pixels of your annotation are very redundant. So the annotation information that you provide in one segmentation or one instance segmentation, it's actually, I'm willing to make the argument, and I have actually some data showing this, that it's quite redundant. So you don't want to be spending time on annotating the left side of a dog and the right side of a dog it's basically symmetric, right? So if you learn to segment the left side, your model will know how to segment the right side. So that's the other argument of why at scale, in the limit, with the supervised learning should be just as good and effective. So you want to avoid redundancies. You do want to account for engineering costs when you're trying to make this decision that the questionnaire is asking. Another point I wanted to add to the June's question, to June's comments, is that the question is missing transfer learning as a bootstrapping element, and that is, I would argue, if you're allowed in the environment where you are due to licenses to use some of the existing datasets, and nowadays that's true for many datasets have very permissive licenses, then the very first thing you should do is to check out which other datasets already exist that are somewhat similar to you, and use that as pre-training. And it's mentioned on the videos, and I keep repeating it all the time. Just boosting the quality of your pre-training is one of the cheapest way to boost your quality. and it's also involved into annotation in the loop. And depending on what you're doing, it might also be involved into your weak supervised learning. So it's kind of most likely to be a win-win-win, and energy should be put in that. Is relatively low effort, big win. And maybe the last comment I want to add into this question is that the question also makes in my eyes makes a bit of a confusion, because it asks specifically to get the best quality and the best performance. And actually these are two different things, and you should be wary about what exactly you're asking for. So in most application domains I'm familiar with, what people actually are interested in is the best performance, right? There's some metric that hopefully translates into dollars, and that's the thing you're trying to optimize. And anything else is beyond the point. Right? How do you maximize dollars? And even if you look at medical applications, you can convert the medical error or someone being sick into dollars. So that also holds for those scenarios, like so economic value in general. So in that sense, the best quality of data only makes sense if it's enabled to have better models, right? That's the only scenario where it matters. And that's a point that we did not discuss in this tutorial, because we have to keep the scope limited at some point. But I think it's a very interesting area, and it's also an area I don't think there was a tutorial. Maybe next conference. Next conference, I might look into making a tutorial into these noise labels, right? We mentioned already a couple of times in the Q&A. And it is adjacent topic to weakly supervised learning, and it is a quite important topic, because if you think about how can you accelerate the annotation, you can accelerate the annotation by annotating differently, and oh, believe me, that makes a huge difference. You can accelerate annotations by asking a different question, which is usually what weakly supervised learning does. It asks a different question that can be annotated, can be answered quickly, or you can force the annotators to go faster, and then accept the fact that it will be noisier. Just go faster or just go rougher, or you force them to be rougher in some way, which allows you to have more annotations, but that will be more noisy. And back to the previous point that current architectures are naturally denoising, and there's some theoretical understanding that why that must be, and what kind of priors are baked in, and how does it learn that, then that might be another way to actually accelerate in practice, right? In practice, that matters. So for that, there's a paper. Okay, let me try to share screens again. I don't think it's very private, the topics question documents we have. So let me show you that. So I guess you see this. So there is this CV Pearson 18 paper, which is again one of my papers I really liked. It's one of the papers I remember highlighting from that conference, which explicitly explored this question. And it's close to my heart because, as I said, I was part of the Cityscapes team. And one of the characteristics of Cityscapes is that we explicitly did both type of annotation. So the dataset is well known for the upper part of annotation, but there's like a factor 10 more annotations of what we call rough annotations. And the hypothesis was that this will enable research in some form of noisy labels or weakly supervised learning. And this paper kind of builds on that and explore this question. And basically what they ask is they say, let's take very high quality annotations and artificially make them worse. So they just basically simplify the polygons. And to be fair, this is one type of noise, but it's I think a nice type of noise because they never wrongly label. They only roughly label. But anyways, it's some form of rougher annotations. And then they try to explore where is the trade-off, right? If you make it like rougher, then the model gets worse. And then you can also mix it and have some fine annotation and some rough annotation. And I'm not going to go into details in explaining these plots, but the long story short is that the mix was the best. They noticed that there was, at least in their experimental setup, some kind of a constant. Like at the end, it was the total amount of human time. And then if you did it one way or another, it didn't matter that much. But if you were trying to push the envelope, the best was to have coarse annotations plus some small annotation, small volume of fine annotation, which in a sense kind of fits the intuition that most people will have. But this is one paper who actually has experiments around it. And I don't think they translate to every single setup, but it's one data point for that. So back to the question that was asked, in a sense, most likely what's going to work is first keep it simple. And if you're really trying to go at scale, then you might consider doing weakly supervised, and then a bit of fully supervised, exactly how June explained, plus a bunch of weakly supervised, that will help. And maybe one last point I want to mention, so we have a bit of time, is this aspect of for crawl data. In the weakly supervised learning video, there's a section that talks about webly supervised, and I invite you to check that paper because that paper has a simple but very, in my eyes, very nice formulation. How do you tackle the denoising problem that June mentioned? So it is absolutely a problem, and if you look at that part of the video, you will see that it's both a problem and a solution. So it has good parts and bad parts, but you have a domain shift that you need to account and maybe exploit, but definitely account. And there's techniques I think that work relatively well and really easy to implement that will handle that. So it's something to consider and to include in your system, but I wouldn't be too worried about that. I think that that's fine. You can leverage that and then eventually get better there. And no, I myself, I work at Google, so it's a topic that we once in a while look into, and I'm looking forward to submit some papers on specifically that. I think that can be exploited and leveraged. All right, I think that covered well that question. We have one more live question, and we have 20 minutes left. So maybe let's do the live question first, and then we jump back to making sure that we cover all the form questions.
Yep.
Do you want to read it, June?
Yes. So it's a question from Sergey. In the context of active learning, what do you think is the next in research direction? As far as I know, I see the research direction is focused on the acquisition function that is task specific, ensemble variation ratio for classification, another different acquisition function for another task. Is there a one-size-fits-all approach for active learning that is task agnostic? Rodrigo, do you want to answer this question?
Yes, let's jump into it. So to be fair, I don't think I have a great answer to this. So let me do free flow thinking about it. So I agree that with observation that it's somewhat focused. Also, you might have seen in the video, I have a mitigated opinion of the field as of right now, which is fine. Like this is literally research, and it's fine that we, as a community, as mankind doesn't quite know all the answers to everything. So an active learning, I think, is one of the things we're still trying to figure out, and it's also one of these things where there's kind of a gap between theory and practice. We have a lot of techniques that are theoretically better, but not in practice, and vice versa. There's some stuff that works in practice that is not quite clear why it should work that well. So I think it's an area that is somewhat doomed to improve because we're a bit in the early days, in my view. And also, if the way I see the field evolving, then this will become more and more important, right? In a sense, also June hinted at this in the previous question, is that at the end of the day, you want to choose what to annotate might matter as much as how do you annotate the bulk of data you have, right? In a sense, nowadays, in many domains, you're close to having infinite raw data, and it's annotation that costs, and then you want to target it. So active learning, and that's the reason we included it in the tutorial, I think is kind of a big part of the story in practice, and something that should be not neglected. So if I had to guess what is one technique that is likely to pay off and to be one size fits all, it's of course what has worked, what has brought us to 2020, right? It's like learning whatever you need to do. So if there's one thing that we have learned in the last 15 years of computer vision, and I think in general, engineering in general, is like if a human design it, it's very likely to be either straight wrong or suboptimal. Right? If a human design it, it's very likely to be suboptimal. So everything that we do better is something that we design an optimization problem that then the machine provides the solution for, and that's what is the outcome. So we still fail on designing the right optimization problem, but we're a bit better, right? So in a sense, the quest for human improvements is a meta quest, and the meta of the meta and the meta of the meta. So there are a couple of papers who did active learning, and this, a couple of variants. They have one specific slide on the talk where I talk about this, and there's links to it. And if you open the PDF, the links should be clickable, so you can jump into those. As I said, they don't work yet, but in theory, they should work, right? In theory, that's the way you go. And that's true if you do also kind of this meta learning. So not only learning to do active learning, but you can do meta learning of active learning where you have multiple tasks, right? So you can basically learn to do active learning over diverse tasks, such as when you encounter a new task, you are not too bad at doing it. There's also one more paper maybe worth mentioning on this is there's a paper that I mentioned in only one slide. It's one of my colleagues. I'm not getting, so Michael Gigley is one of the co-authors, and I'm finding the keywords in my mind, but it's basically a paper who showed that as you're collecting annotations, in this case was for instance segmentation masks, then retraining the model as you collect data is a way to get better questions and better results. And that also applies for learning to do active learning. So it's another form of meta learning, right? You can meta learn through the task, but also you can learn while you're doing your annotation campaign. And I think these kind of strategies where you're learning to do your active learning, and as you collect data, you're learning that. That is, it hasn't worked yet, but conceptually it has to work, right? It has to get there and work. One of the formulation of this is a reinforcement learning version of this, which also has been proposed and also works not quite yet there, but we're going to get there. So this back to the story about engineering versus benefits, right? So right now it's a lot of engineering for almost never good benefits, but eventually we'll figure out this kind of ResNet version of it, which is like simple enough and good enough that will make it worth it. So that's my mindset on this. Right. So let's answer the other form question we had. Mm-hmm. So I will. Oh wait, actually we have two more, and we have 15 minutes. Okay, so let's make sure we cover this because it should be there. So let me start with Ayush question. When we talk about learning from few label examples, like one label example per class, how do we choose the representative for that class out of so many candidates? Okay, that's exactly what we're discussing. That's perfect. Yep. In CVPR 20, we uniformly randomly choose k samples per class.
Yeah, that was my answer. Yeah. I wrote the answer at the bottom. So that was my word. Yeah. Exactly.
And then you have, I see, got it.
So yeah.
Right. So maybe you can start answering then.
Yeah. Well, we do the choice of the samples to annotate at uniform random. But as you probably have seen in Rodrigo's talk, it's probably the dumbest strategy, and probably using some other ways to select samples will work better in this case. But we just went for the simplest choice, and we have made a point already by using this dumbest baseline that even in that case you're beating many WSOL methods in the benchmark. But yeah, so we do uniform random choice of the samples.
Yeah, and as Jun said, do check the human in the loop learning talk. Is not that long, and this section we're talking about other strategies that can be used, and they work to some extent. It's I will still say because I'm a big fan of baselines, uniform sampling works quite well still, right? It's like you always want to at least run one experiment with that, and you would be surprised how well that is. So the representatives for the class depends of the nature of your class distribution, right? So if you have, let's say that you have only one type of dogs that you care about, like you have multiple dogs, but that among all the classes you have one type of dog. So then any picture of that specific type of dog would be very self-similar to all the other ones. In a sense, which ones do you pick doesn't matter much. But the other extreme is the version where you had 1,000 instances of one type of dog, and then only one single instance of the other type of dog that you care, all in the class dog. And in that case, if you just take a random sample, you're likely to repeat the same thing, and you would very likely to miss this extra variant of the dog that you care to capture. So then diversity will matter to capture, and then you want something smarter in your sampling process. But that scenario, the second scenario mentioned, where it's kind of very skewed in the appearances, is actually quite rare. In practice, most categories either are very, very self-similar. Let's think about ostrich, right? Basically, most ostrich looks the same, at least to my eyes. And if you have multiple variants, let's say, okay, dog types, then this tends to be somewhat uniformly sampled, right? Like the different type of boats, the different type of airplanes. It's not that common in the natural world that you have something that you do care about that is somewhat rare, and that was not already reflected in how you collected your data or how you define your classes, right? Because another typical strategy is to say like, well, no, actually I do care about this kind of boats, and then you have fine-grained boats classification, and then you collect in your data sets, you're going to explicitly make sure that every kind of boats have 10 images at least, and then within those you can do uniform sampling again. So in a sense, that's one of the reasons why uniform sampling works well, because the dataset construction already kind of baked in the fact that uniform sampling should work well. So yeah, so that's kind of the mindset. And if somehow you're in the other scenarios you care about, look for the things I really talk in the talk. And maybe one last thing, and then we move to the next question, is that there's an aspect of diversity in your sampling. And didn't talk it in the talk because it was only 20 minutes at the tutorial. I want to keep it simple. And there's quite a bit of work on diversity sampling. The keyword there is determinantal processes. you can look for that. DPP is usually abbreviated, and it's one of the things, again, there's like quite a lot of literature. There's quite a lot of very interesting theoretical work, and in practice, it's hard to make it work in practice. I don't remember having seen a paper where it's like, oh yeah, no, this really works. But it's something that in theory you really want to have, and in practice, it's hard to get it well. The diversity into samples you have captured, and the reason it's hard is because you don't know what should be similar and what's different before training your model. But that's a story for another day. All right, let's move to the last question. Jin1. Well, okay, probably June can read this better, but okay, let's go with Jin1. Asks, hello, sorry about that. I have a weird name myself, so I'm sensitive to butchering other people's name. Sorry about that. Hello, I have some questions on the weakly supervised object detection methods. The first one, with respect to detecting multiple instances, state-of-the-art methods use simple algorithm to find multiple positive labels, but I think it is heuristic and still remains a limitation. What is your opinion detecting multiple object in a weakly supervised object detection setting? And then there's a second question. From my poor aspect of this problem, I guess my poor understanding of this problem, I think that normalized over detection in WSGDN seems to be biased on increasing only one positive instance rather than select multiple instances. What do you think about this issue? So this is the kind of question that Hakan would be best to answer. And we might ask him if he joins us in the second slot. So that will be check the recording of the second slot in case for maybe a better answer. But I can give it a shot at this. So the first one is that, yes, you're completely right. It is harder, and it is definitely heuristics. Welcome to computer vision in 2020. That's mostly what we do, right? Like we see that the problem is very hard, and then we either simplify it, we correctly solve the wrong problem, or we wrongly solve the right problem. That's where we are, and that's likely where we'll stay for a very long time. And some of the ways to wrongly solve the right problem is to use heuristics. And in a sense, some of the insights, the transition between computer vision in the 2000s and in 2020 has been this transition from exactly solving the wrong problem to wrongly solving the right problem. Turns out that the second one pays off way better. And this frustrates a lot of theoreticians, but no, welcome to real data. So I would say that it is a heuristic, but don't look it so bad. That's fine, right? If it works and it gets good results and it's a good way to bake in your priors about the problem, then that's okay, right? It's not to be dismissed because it's an heuristic. I think the better question is like, well, is it a good enough heuristic? And what will be a better heuristic? Which information?
A good heuristic, but I think more recent work, I think I mentioned in my slides and in my talk, so they kind of use WSDN to initialize their detector, and then they take the highest scoring windows and generate multiple clusters in a positive image. So this way, then they can transfer these bounding boxes, multiple bounding boxes, to faster RCNN or faster RCNN kind of supervised method. So then you can actually use multiple instances. But it's true that because the method builds on WSDN, it is biased to detect only one.
Okay, so let me see. Yeah, I guess I will have had a similar, at least the last comment, it will be similar in my mind also, that at the end of the day, maybe the one thing I can add is that this weird thing, this basically a relation with curriculum learning, in the sense that many of the data sets that we have started evaluating on, things like Pascal, actually don't have that many images with multiple instances, and not so many images with multiple instances of the same class. So that's one of the things, one of the reasons why the methods have been developed kind of with this strong prior about, well, doesn't matter if we handle that well, the multiple instances. And then you can think of it like, if you know that, if you know you have a data set that is somewhat simpler images, then you can just kind of pre-train your model, let's say on Pascal, and then you can use that model weakly supervised, right? And then you can use that model as a general object detector that then you run your next data set, which might have more complex images with more instances. And because now you already have some general notion of object, you can get going with that. So in a sense, you can also escape this strong prior by having either an implicit or explicit kind of curriculum learning like approach. And basically, many of the methods that use these proposals implicitly are doing that, right? Because the proposal was tuned or trained somewhere else, so that then you have the initial boxes, and then from there on, you only have to figure out which ones are noisy, and then which one have the right class. But it significantly simplifies the problem. So that's kind of another aspect where this is being leveraged. And in a sense, remains to be seen how well we can push the envelope when we get into even more complex data sets with even more classes. But yeah, that we'll see, and I guess in the next few years. I'm not too worried. I think this is something we can tackle at the very least through this curriculum learning approach. Okay, maybe since we have a few attendees who did join back, and we're anyways reaching the very end, does any of the attendees who have sticked with us through the whole talk, not just dozing off, and did join back, do any of you have some last question, last thing you wonder about? Otherwise, we'll just close the session, and then there will be a second slot later in the evening. Some of you might be able to join, otherwise other people will join. Any last questions from the audience that you can put in the chat? Otherwise, in the meantime, any last comments that either Hakan or June wants to add to this session?
Yeah, I guess now that we learned how this Zoom works, the second session will be much better. In terms of,
I'm not putting my hands on fire for that one. I think we'll do our best, and we hope it goes a bit smoother. Very sorry about the drop in the middle. That was certainly unexpected, and I hope at least the sound of my voice was a bit better. Thanks a lot for joining us. It really makes it a lot more enjoyable to talk with 7 attendees. As I said, my initial goal was 3 or more, and then talking in the voids and just have a recording. And thanks a lot for all the very interesting questions. I think it really was interesting. And then, as we said, maybe see you in the next slot, and we'll keep the discussion, and we have the extra points. And if we manage to recover the recording, we're going to anyways put the recordings on YouTube later on. So thanks all for joining, and have a great very last day of ECCV.
Thanks.
Bye.